Our next speaker is Nandana Bhattacharya from Indian Institute of Science, Bangalore, and she is going to tell us about site-selective polar compensation of Mott electrons in a double perovskite heterointerface. Nandana, the floor is yours.
Good afternoon, everyone, and I thank the organizers for allowing me to present our work on site-selective polar compensation in a double perovskite heterointerface. So this is a brief outline of my talk where I'll give some basics of electrostatics and a consequence of satisfying the boundary conditions at interfaces, which is commonly termed as polar catastrophe, and how it manifests in semiconductor systems versus oxide heterostructures. And I'll move on to the system that we are studying, which is a double perovskite system and the polar catastrophe in it, how compensation of polarity is happening there. And finally, I'll discuss about what is the role of correlated physics in this compensation mechanism. So in electrostatics, we know that if we want to satisfy the electrostatic boundary condition between two dissimilar materials across the interface, then the potential should be continuous. And by the dissimilar materials that I am talking about, they can have different kinds of polarities. That is, they can have different charge distributions. And when we solve for the potential from the charge distribution, we can get different types of interfaces. So we can broadly categorize them into these four categories. And if you look at the type 2 and type 4 kind of interface and the corresponding potential profile, you find that across the interface, the potential is diverging. And this phenomena is termed as a polar catastrophe. Now in nature, such a diverging potential is unstable. So some kind of reconstruction or compensation of polarity happens so that this divergence is gone. So the study of this polar catastrophe began in the semiconductor heterostructures with gallium arsenide germanium heterostructure being studied in great details. And initially people suggested some kind of an electronic or charge reconstruction from theory. But experimentally, people could not find any kind of electronic reconstruction here. And finally, what was presented here was some kind of a stoichiometric or chemical rearrangement. So basically, the germanium and the gallium and arsenide, these atoms, they rearranged across the interface to compensate for the polarity. Now, this was equivalent to saying that in a semiconductor, these atoms which are like more elemental in nature, they cannot access multiple valence. And that is where complex oxides are fundamentally different from semiconductors, because here we have transition metals which can access multiple valence states and give a broader regime of compensation mechanism. So gradually the field extended to the field of complex oxides, and I'll take a very well-studied example of lanthanum aluminate grown on strontium titanate. And if you look at the substrate side, we have this SRO and TiO2 kind of atomic layers, and these are all charge neutral. And on the film side, we have this +1 -1 kind of a charge distribution. So this resembles like the type 2 kind of interface that I was talking about, and a polar catastrophe is seen here. So this polar catastrophe is compensated. One of the proposed mechanism is that an electron comes from the surface to the interfacial titanium atom with half an electron per unit cell contribution, and this divergence of potential is lifted. Now gradually this began to be studied in many other complex oxide systems, and it was found that a number of reconstruction mechanisms like electronic reconstruction, oxygen vacancy formation, cationic intermixing, etc. could be possible. Now as a result of such reconstruction mechanisms, a number of emergent phenomena could also be seen at the interfaces, like the formation of two-dimensional electron gas, interfacial ferromagnetism, superconductivity, and so on. But one point that could be noted is that when we are discussing about the compensation mechanisms, even in complex oxides, we mostly look at it from a semiconductor-like band bending framework. But actually these transition metal oxides, they have a very crucial set of energy scales which are coming because of electron correlation. So a very important question that we can ask is, what is the physics of strong correlation in the polar compensation mechanism? To briefly give an idea about the energy scales, when I'm talking about the transition metal oxides, we can have the on-site Coulomb repulsion U, we can have the charge transfer energy between the oxygen and the transition metal cation delta, and of course the hopping interaction strength. And if I take a parameter space of the U by T and delta by T parameter, we get a phase diagram of the transition metal oxides, which is also known as the Zanen-Sawatsky-Allen phase diagram. Now the question in hand is, how will we specifically determine the role of electron correlation in the polar compensation? Because as I discussed in the previous slide, like the lanthanum aluminate and strontium titanate, then on the film and the substrate side, we had one transition metal cation. And that one transition metal cation will have its one set of U, delta, and T. So what we can rather do is that we can choose a system which has more than one transition metals, for example, a double perovskite. So here, this B and B dash, which are my two separate transition metals, they can have their own set of correlated energy scales. And our hypothesis is that if correlation physics indeed plays a crucial role in this compensation mechanism, then this B and B dash may react differently to the compensation mechanism. And also this class of double perovskites is a very exciting class of materials themselves because they show some very interesting properties like high Curie temperature, ferromagnetic insulating state, multi-glass behavior. And the study of polar compensation in these systems is at a very initial stage, and it would be very interesting to explore them in itself. So the system that we are studying is that we have chosen a double perovskite Nd2NiMnO6, which is an insulating ferromagnet with Curie temperature 200 Kelvin. And more importantly, we have this nickel and manganese, which have different correlated energy scales. So this is my plot for U and this is my plot for delta. So these orange lines. So we see that manganese and nickel have their own set of U and delta. So what we are doing is that we are creating a heterostructure by growing thin films of this Nd2NiMnO6 on neodymium gallet substrate and strontium titanate substrate. So in the first case, there is no polar mismatch, while in the strontium titanate case, we have a similar scenario like the lanthanum aluminate strontium titanate case, and we have a polar mismatch here and hence a polar catastrophe. So we will comparatively study these two cases to finally pick out what differently is happening in the case where we have polar catastrophe. So we have grown thin films in our lab using the pulse laser deposition technique, and it works basically on the principle of laser ablation of a solid state synthesized target, where a plasma plume is formed where the material is deposited on a heated substrate, and we can monitor the thickness of the unit cells via a reflection high energy electron diffraction read, which already Professor Jalan has mentioned. And the advantage of using our system is that, first of all, we grow very ultra thin films as low as 1 to 2 unit cells, which we can monitor via the read. And the chamber, in this chamber, we can grow up to a very wide range of pressures like ultra high vacuum of 10 to the minus 9 torr, or even hundreds of torr when we are growing in gaseous atmosphere. And most importantly, we get very excellent film quality, which are even comparable to the quality that we find in molecular beam epitaxy films. And that's why this method is also known as laser MBE. And I'll be showing the quality of the films very shortly. So here I'm showing the characterization of one of the films that we have grown, which is a 20 unit cell Nd2NiMnO6 on strontium titanate. And we see a very prominent film peak here with excellent thickness fringes, which tells us about the excellent crystallinity of the film. And also from the reciprocal space mapping, we can see that our films are perfectly epitaxially strained. Now we have also collaborated with Professor Yang's group to get results from scanning transmission electron microscopy. And this is a high angle annular dark field imaging. And the bright atoms that you see on both sides are the rare earth atoms, which has higher atomic number. Like on this side, the brighter atoms are strontium atoms. And on this side, they are the Nd atoms. And we see that we have a very clear, sharp atomic interface, which is, the film is devoid of any defect and dislocation. We have further performed elemental mapping using electron energy loss spectroscopy, where we are mapping the individual elements. And what we find is that the intermixing scale across the interface is very small. And also, very importantly, there is a uniform distribution of manganese and nickel throughout the film. So basically, what we can tell from this is that nickel and manganese are at equal footing right now. There is no clustering. Now, for the polar compensation in transition metal oxides, one very important thing that is mostly noticed is a change in the electronic structure of the transition metal cations. So to probe that, we have performed X-ray absorption spectroscopy at advanced light source at the L32 edge of the transition metal cation. So first we probed on the substrate side, the titanium edge, and what we find is that titanium remains titanium 4+, just like bulk strontium titanate. So these are different thicknesses of the film that we have grown on STO. And then when we moved on to the films on to the nickel edge, what we find is that for all thicknesses on both NGO and STO substrate, nickel does not change its valency. So irrespective of whether there is polar mismatch or there is no polar mismatch, nickel remains inert to the process. So nickel behaves like bulk nickel 2+ in Nd2NiMnO6. So another thing that we also checked is that we bonded the interface via wire bonding, and we found that the interface is insulating. So there is no metallicity or two-dimensional electron gas forming in our case. Now the interesting thing was observed for the manganese states. So I first discussed the case for the films on NGO where there is no polar catastrophe, and we find that for all thicknesses of the films, we get this manganese 4+ like bulk states, and we also get signatures of this manganese 2+, which increases or becomes more prominent as we go down the thickness. Now we can attribute this to some surface manganese states because it is very commonly observed in epitaxial thin films of manganites that some states on the surface become manganese 2+ because of surface symmetry breaking and because of absence of the apical oxygen. And I will discuss later how also we are attributing exactly to the surface. On the contrary, if you look at this series of films of different thicknesses on STO, we find that apart from the manganese 4+ states that are like bulk-like and the manganese 2+ states that we also found here, which can be attributed to the surface, if you follow this middle blue line, this is a signature of manganese 3+, and it increases as we go lower in thickness. And specifically, if you compare the 5-unit cell film on the NGO and the 5-unit cell film on STO, you will see how clearly this manganese 3+ state is emerging. Now this is the distinguishing factor that we get between the two cases, where in one where there is no polar mismatch and the case where there is polar mismatch. So we can attribute it to some charge compensation happening selectively at the manganese site. So now we know that these different kinds of charge states are present in the film, but we can still, from the XAS experiment, we cannot say where these charge states are located, like whether they are distributed uniformly throughout the film or they have some presence near the interface or surface and so on. So for that, we need to check what is the layer resolved oxidation state of the cations. So for that, we go back to STEM yields and look at the yield spectra. So first we look at the titanium. So for titanium, this is like the interface region and this is the bulk-like region. And we see that titanium remains like 4+ state for both bulk and interface-like region. Whereas for the nickel, if you look at this A, this is like interfacial region, then B bulk-like, and C is the surface-like region. So what we do for this analysis is that after taking the spectra, we take the ratio under the area under the L3 and the L2, and we take their ratio. And this number directly maps on to the oxidation state of the cation. This is a very well-known technique that you can also find it here. It is used in yields very extensively. And from here also we see that in all layers, nickel remains nickel 2+. Now for manganese, when we look at the manganese yield spectra, and we do the same exercise here with the area correction, and we also take average over some regions for better statistics. So this is like a layer resolved, so if you consider the 0 as the interface, so this is the layer resolved charge state of manganese. So you see that near the interface, the character of the manganese cation is more 3+ like. In the bulk region, it is more like 4+. And as we go towards the surface, it becomes more like 2+. So this is how we were attributing the manganese 2+ as to the surface states. So this can be further supported. Yeah, so this can be further supported from the high angle annular dark field imaging. So as I was saying, the bright spheres that we see here, these are the rare earth cations. So the interatomic distance between two neodymium, it gives me my out of plane lattice constant. Similarly, interatomic distance between two strontium gives me my out of plane lattice constant on the substrate side. So now if I look at the layer resolved out of plane lattice constant, we see that it is slightly enhanced near the interface, then it becomes to its lower value, and near the surface it becomes very much enhanced. Now this can be explained by Vegard's law of crystallography, which says that the out of plane lattice constant, it is directly proportional to the ionic radii of the cation. So if you look at the ionic radii of manganese 2+, it is the most. That's why we have the most enhanced out of plane lattice constant near the surface. And for 4 plus, it's the least, and that is what is happening in this bulk-like region. And the intermediate one is like what is happening near the interface. So now we can propose a mechanism that is happening just from the XAS, STEM measurements and by simple charge conservation of the various cationic states of manganese that we have got. We can propose a very similar mechanism from an ionic perspective as we had in the LAO-STO case. So we can say that half an electron per unit cell contribution is happening towards the manganese states near the interface. And if we also look at the band bending picture of NNMO-STO, so this has a lower band gap and this has this kind of a straddling band configuration, and an electron can come from this potential gradient and it can accumulate near the interface. But this simple band bending does not tell us that why the electron is getting added only to the manganese site and the nickel is remaining inert. So for that, we invoke the physics of electron correlation. So based on the U and delta values that I had shown in the previous slides for nickel and manganese, we can draw the band structure of this Nd2NiMnO6 in the light of the Hubbard bands. So the upper Hubbard band are the unoccupied bands and the lower Hubbard bands are the occupied bands. And if you look at this one, then you see that manganese upper Hubbard band is at a lower, energetically lower value than the nickel upper Hubbard band. So when an electron, if an electron is intending to get added, it will see the manganese upper Hubbard band first. And that's why it selectively prefers to come here. And after the electron has been added, if it completely turns into Mn3+, then there is a shift of this manganese upper Hubbard band to a higher energy. Now this can be experimentally also visualized from the oxygen K-age excess. Yeah. So the oxygen K-age excess basically is a measure of the density of states above the Fermi level. And if you follow the pink shaded line here, where you can also see a peak here, you see that as we go lower in film thickness, this peak keeps on decreasing. So this, and also if you look at the blue shaded line here, we see that there is an enhancement in the peak as we go lower in thickness. So this is very similar to what I was showing here. So initially for say a 20 unit cell film where you will see more of manganese 4+, you have a high DOS. But then as you go lower and lower in thickness, you have more manganese 3+, and there is a spectral weight transfer from this peak to this higher energy peak near the nickel upper Hubbard band. So that's what we can also understand experimentally. Furthermore, we have collaborated with Professor Umesh Wagmare's group to perform some DFT calculations, and we have looked at GGA and GGA plus U calculations. So you see that when we are not considering the U parameter in the calculation, the unoccupied states for nickel and manganese, they are similar in terms of the energy where they are standing. But when we are putting this U term into the calculation, we see that manganese becomes closer to the Fermi than the nickel, which goes away in the energy. So this also tells us how important or crucial this U parameter is while determining which is the closer unoccupied density of state near the Fermi. So with this, I would like to summarize our results that what we find is a site-selective charge compensation occurring at manganese site in a double perovskite film exhibiting polar catastrophe. And so our results also demonstrate how the role of correlation scales is very important when we have two transition metal cations coming into the picture. And lastly, one important thing that our result can do is that it works as a designer's tool. So now this BOB dash, this kind of bond that we have, that it becomes tunable. So if we know, so of course we can guess what is the U and delta for the specific transition metal cations. And based on what phenomena we might want to design, because we know that this electron gets selectively added, we can use this method as a designer's tool to create our own heterostructures for a desired mechanism. So our work is there in archive. You can look at it if you wish. So with that, I acknowledge my lab members, Professor Srimanta Middey and all my lab members, and the facilities that we have used, Argonne National Lab and Berkeley Lab, and our collaborators, Zhenjiang Yang, Professor Umesh Wagmare, and the funding agencies. And with that, I thank you for your time.
Thank you. Any question from the audience?
Yeah, thanks for this very nice and clear talk. So what happens to the ferromagnetic state with this magnet 3+? So is there a new kind of mechanism appearing?
Yes. So we are currently studying that. So you see already this nickel 2+ oxygen Mn4+, that is a ferromagnetic super exchange. And recently we were doing experiments on the thickness dependent films. So what we find is that we get a very much enhancement of the ferromagneticity in the film. That might be because we have this Mn3+ oxygen Mn4+ kind of a coupling also coming. Now that I have my Mn3+ here, we can also have this kind of a coupling, and that is also ferromagnetic in nature. So that can enhance the ferromagnetism in the system. So we are currently studying that, yeah.
Any last question before the break? Yes.
We can talk more, but your TEM pictures, the atoms look square rather than circular. So there's something else going on if you zoom in.
Yeah, probably in the lines of distortion, yes. So I can probably show you
It's
some
either,
results.
yeah, some aberration, or it might be actually two atoms or multiple atoms overlapping.
So yeah, one thing that we have on the film side is that we have this A-site antiparallel displacement. So that can cause an overlap between two atoms, like from the back and from the front.
Right. So, otherwise, it should.
But
They all look like squares, actually, from here at least.
Okay.
So it's interesting. Something is interesting there.
Yes, sir. Okay, I'll look into it more. Yeah.
Let's thank all the speakers of this session.